In this example, I would like to diagonalize our matrix. A is equal to the 2 by 2 matrix. First row is negative 2, 4. Second row is 1, 1. Now, you may recognize this as the first example from the playlist for section 7.1. As such, I am going to point out that we have already found the eigenvectors and eigenvalues. One of the eigenvalues that we got was lambda is equal to 2. The corresponding eigenvector that we got for this was v is equal to, and I'm going to write it as a column this time, 1, 1. The other solution that we got was lambda is equal to negative 3, with the corresponding eigenvector being negative 4, 1. Now the idea is we are going to be creating a matrix that we're going to know as P. P is going to be comprised of the two eigenvectors set up as columns. So I'm going to set up 1, 1 for the first column, representing lambda is equal to 2. And I'm going to represent 4, 1 as the second column. That'll be for lambda is equal to negative 3. Now the idea is, if we multiply P inverse times A times P, this should wind up giving us a diagonal matrix of eigenvalues for our answer. So 1, negative 4, 1, 1, inverse, multiplied by negative 2, 4, 1, 1, multiplied by 1, negative 4, 1, 1. Now this is once again where a calculator is going to come in exceptionally handy. So I'm going to grab my graphing calculator. I'm going to plug in A as my matrix A. So I'm going to edit a 2 by 2 matrix. That'll be the matrix negative 2, 4, 1, 1. Then, re-entering the matrix menu from the main menu, I'm going to edit the matrix B to be my matrix that we're referring to as P. So once again, a 2 by 2. This is 1, negative 4, 1, 1. Exiting out of this, I would now like to ask my calculator to multiply B inverse times A times B. I enter the matrix menu, I select B, then I press the same button that got me into the inverse menu, which is the multiplicative inverse button. That is now referring to B inverse. I multiply this by the matrix A, and I multiply this by the matrix B. If all has gone well, I should see a diagonal matrix of eigenvalues of A. This is the part where you cross your fingers really, really hard, because if you screwed up something, you'll know right away. However, when I press enter, I see exactly what I predicted that we would see, which is 2, negative 3 along the main diagonal, and zeros everywhere else. It should be pointed out that the 2 being here and the negative 3 being here is predicted by the relative positions of the eigenvectors. We did 2 for the first column and negative 3 for the second column. Now this also means something else. That means that if I were to create P in a different fashion, sorry, knocking over some cat treats here. If I were to construct P in a different fashion, where I put lambda equals negative 3 in the first column and lambda equals 2 in the second column, this is a different but still valid way to diagonalize our matrix. It just means that when we do so, the 2 and the negative 3 will be in the opposite positions. So, once again, we'll multiply P inverse times A times P, which will be negative 4, 1, 1, 1, inverse, times negative 2, 4, 1, 1, times negative 4, 1, 1, 1. Now, because we used the graphing calculator for the last one, I'd like to reuse it for this one. Good news is, I've already typed in what the matrix A is. We'll just go ahead and verify that that's still the same as it was before. The negative 2, 4, 1, 1, negative 2, 4, 1, 1 looks good so far. We are, however, going to edit the matrix B. Still a 2 by 2. We'll just make the 1, 1 entry negative 4 and the 1, 2 entry 1. Everything else is as it should be. So negative 4, 1, 1, 1, negative 4, 1, 1, 1. Now, using one of the special features of the graphing calculator, I'm going to arrow up until we get the expression that I want to use once again. I'm going to press enter, and that's going to recopy it into the current line. Now here's the part where you cross your fingers real good and you press enter and hope for a diagonal matrix of eigenvalues, which is precisely what we got. Now once again, we predicted the positions of the -3 and the +2 based on the relative positions of the corresponding eigenvectors. So -3 for the first column, 2 for the second column, as we predicted right back here. -3 for the first column and +2 for the second column.